Exercise 5 is about the relationship between the pseudo-inverse and the full inverse, and also between the pseudo-inverse and a one-sided inverse. And what I explained earlier in this chapter is that those are equal when the matrices have their maximum possible rank. So for a full rank matrix, the pseudo-inverse is the same thing as the full inverse. And for a one-sided inverse, the pseudo-inverse is the same as the left inverse for a tall matrix, assuming it's full column rank. And the pseudo-inverse is the same as a right inverse for a wide matrix, again, assuming that the wide matrix is full row rank. So there's ways to prove that rigorously with a piece of paper and a pencil. And what we are going to do in this exercise is demonstrate that empirically to help you gain intuition for the pseudo-inverse. So here I am creating a full rank matrix, a 4x4 matrix. So this matrix will have a regular full inverse, a two-sided inverse. And that's what I compute here. And then here is the pseudo-inverse. This function pinv computes the Moore-Penrose pseudo-inverse of the matrix. And here I'm subtracting them, and we certainly expect these to be zeros, assuming that they are the same, which they are to within a reasonable degree of rounding error. Okay, so that's the full inverse case. Here is the left inverse case. So you can see I'm creating a non-square matrix, a rectangular matrix that is 14 by 4. So this is a tall matrix. It has 4 columns. Because these are all random numbers, I expect this to be a rank 4 tall matrix, which means it doesn't have a full inverse, but it does have a one-sided left inverse. And that's what I create here. So the inverse of A transpose A times A transpose. And when this is put on the left side of A, we will get the identity matrix. Okay, so here's all this crazy stuff written out. Okay, maybe not as crazy as the earlier exercise where we wrote out the entirety of the algorithm for computing the inverse, but you can see this is certainly a lot simpler. This is a lot less code. It doesn't involve computing the explicit inverse, which is also quite an advantage. Okay, so we have A left here and a pseudo inverse over here. And again, we are just going to subtract these two matrices and find that they are zeros. Now, this is not a square matrix. These are not square matrices. This is actually a wide matrix, and it multiplies this tall matrix A to give us the identity matrix. The important point here is that we used the Moore-Penrose pseudo-inverse to compute exactly the left inverse of this tall matrix. Now, given those two demonstrations, you're not going to be surprised to see that it also works for the right inverse. So here I have very, very similar code to what I just showed above, but now the matrix is defined as having more columns than it has rows, so it's a wide matrix. And here I compute the right inverse, and here is the pseudo-inverse of matrix A. Again, this is not the pseudo-inverse of A times A transpose. This is the pseudo-inverse of the original non-square matrix A. And of course, these two are the same to within any reasonable degree of computer rounding error. I think this demonstration is pretty neat because among the other kind of theoretically interesting aspects, it also demonstrates that if you need to use the right inverse, or if you need to compute the right inverse, you can use the pinv function instead of writing this and, worrying about whether the inverse here is going to be suitably numerically stable.